Nice. Good afternoon, everyone. My name is Henri, and I will be talking to you about the real reverse engineering. As a heads up, this talk will be very tight on schedule, so tighten your seatbelts and we will get started. This talk talks about the x86 processor architecture, which I assume most of you are familiar with. It executes instructions in a linear fashion from top to bottom. It does this with a special register called the instruction pointer, or RIP, which after instruction is moved to the next instruction, and so you get this natural flow from top to bottom. Of course, this is a little mundane, this is boring, and as a curious-minded hacker, you wonder if we can do things a little differently. The processor also has these special registers called the debug registers. There are 8 of them. We don't care about these 3. The rest are for setting breakpoint addresses and enabling these corresponding breakpoints. So what are breakpoints? If you set the debug registers, these one of the 4 address registers to point to an instruction, and you let execution get to that instruction, the CPU will raise a hardware interrupt, which the operating system catches, and then execution is diverted to the exception handler, specifically a vector exception handler in case of Windows. Inside of this exception handler, well, of course, needs to be registered by the user code, and the handler itself is just another function. It gets information about the exception, the processor state. It can modify the state, and then it returns a status to the operating system, which can either tell it to continue the search for another handler or to continue execution with a potentially modified processor state. Using this, we can do something a little cursed like this, where we get the address of the previous instruction and we jump to that by moving the instruction pointer to the previous instruction. And if we do this repeatedly after every instruction, we basically achieve this reverse code execution, which is pretty cool. But how do we get started with this? I mean, if we have this block of code that we want to run in reverse, we can't just jump into it. The processor won't know to do this in any special way, but we can prepend this custom setup code to it that basically contains information about the real start of the function, which is later, and then some call into the machinery that initiates this reverse execution process. Here it's this call, but because we're working with exception handlers, we can have some fun and instead just trigger some kind of exception instead. So we could do, for example, division by 0, or my favorite, which I ended up using, we can run a virtualization instruction, which obviously is an error in a user space application. So putting all of this together, when we reach this initial signaling instruction, we enable the first 2 breakpoints. We take this address, which is the current instruction being executed, plus the value we just loaded, which, as visualized, was the real start of the function. We jump to it. Then we start this 2-step dance where we basically let the current instruction execute. We move the breakpoint 1 step down. Then we move the breakpoint 2 steps up. We jump to that instruction, and we repeat this to slowly step up our function. And then we reach a return instruction. We clear the breakpoints, and we are done. How do you generate code for this? I mean, you could write assembly by hand, but that's kind of annoying. I mean, you can just compile code normally and reverse it before linking, or reverse specific functions before linking. Of course, you can do this, but it comes with a lot of sub-problems, which are not trivial. They can be done, but it's not pretty. How does this look like from a reverse engineering point of view? Of course, you can throw this into something like binary ninja. Here you see the same structure. You have the function prologue at the start, followed by the end of the original function, because it's in reverse. Of course, binary ninja is expecting it to be executed from top to bottom, so it uses these assumptions to give you some incorrect analysis. This is more clear in the decompiled C version, where it partitions this into 3 separate functions, which doesn't really make sense, of course. You can also look at the function body itself, but again, because this is decompiled from the reversed code, it's not really correct code. In some cases, the C decompiler in Binary Ninja has such a bad time that it actually just gives up and crashes the whole Binary Ninja application. You can look at this in a debugger, and it works actually surprisingly well. You can step upwards the function. But if you're trying to set breakpoints, this will interfere with this dance logic that I explained, and you end up falling outside of the function. So you get different behavior if you're in a debugger with breakpoints. Okay, forget about manual analysis. Let's just detonate the whole thing in a virtual machine. Not so fast. VirtualBox gives up when it sees the virtualization call. So you get this guru meditation exception or error. VMware tries to be clever. It doesn't give you an error, but it also behaves differently than a native host would. So you get different behavior if you're in a VM, which is interesting. So what is the takeaway of this? I mean, this is more of a fun party trick than a useful technique. It has massive execution overhead. And also, if you know that this is being done, it's easy to statically just unreverse the function. Of course, if you put another layer of obfuscation on top, then you might get into a more realistic territory with this. So that was a lot. Thank you. And I hope you learned something new.